In the early 1960s, the young American mathematician Stephen Smale was working on the beach of Copacabana when he made a discovery. He discovered a horseshoe. Not in the sand, of course. In fact, this horseshoe is an abstract mathematical object. It is another simple idea that attempts to reduce chaos to its most elementary expression. We must first explain an old idea dating back to Poincaré. Here is a vector field in space. A trajectory that starts on the green disk must travel all the way around before returning to the disk, and then taking another trip, and so on. For each point x of the disk, we can observe the trajectory that starts from that point, and wait until it hits the disk again at a new point, p of x. A few seconds later, this new point is again transformed by t, and we get a third point, t of x, and so on. After each trip, the point is transformed by t. Instead of studying the trajectory in space, we study the sequence of returns to the disk. This is much easier to draw. We replace the dynamics of the vector field in continuous time by the dynamics of the transformation t in discrete time, 0, 1, 2, 3, and so on. This is often much easier to understand. Here, the transformation t is a rotation by 1/3 about the center of the disk. The central trajectory corresponds to the fixed point of the rotation, the center of the disk. Other trajectories are also periodic, but it takes them 3 times longer to return to their starting point. This is because we are rotating by 1/3. Here, the transformation t is a similarity. The trajectories are no longer all periodic. On the contrary, they approach the central trajectory while spiraling around it. We say that the central trajectory is stable. Here is an example of an unstable trajectory. The transformation t squeezes the kitten along its width and stretches the kitten along its height. The center of the disk is a fixed point, so its trajectory is periodic. You see that the trajectories located on the horizontal axis approach the fixed point, while those on the vertical axis move away from it. Poor kitty. Now let's look at the horseshoe. Watch how this square is deformed over time. The transformation t combines a scaling, a contraction, and also a fold. When the square arrives back on the original disk, it has taken the form of a horseshoe. Now watch the behavior of the square as we go back in time by the inverse transformation. A scaling, a contraction, a folding, but this time all in the other direction. Let's try to envision the future and the past of the square. After one trip, as we have seen, it becomes a horseshoe. After one trip the other way, into the past, it also becomes a horseshoe, but turned by 1/4. The two small vertical strips you see at the intersection of the square and the horseshoe are also compressed, scaled, and folded. The behavior into the past is the same. And this whole structure is repeated an infinite number of times. A very complicated horseshoe. How can we understand its dynamics? Let's call this strip A and this strip B. Well, the amazing thing is that we almost get the same results as Hadamard's geodesics and billiards. For each finite sequence of A's and B's, even when allowing repetitions, for example, BA, BB, there is a periodic point that will follow this route exactly. In this example, we have a point of B that jumps to A, then jumps to B, then jumps to B again, and then jumps back to the starting point. Here is the only point of A that always remains in A. It is a fixed point. This fixed point is in B. Here is a trajectory that alternates between A and B. But, as with billiards, this is not limited to finite sequences. Give me an infinite sequence of your choice, BB, AA, BBB, AA, BA, BA, and so on, well, there is a point following exactly this route in its future. When you think about it, this is incredible. Every possible future is true for at least one person. Oops, I meant for at least one point. Prediction is impossible because everything is possible. Free will rediscovered. Anything is possible? That's a fine slogan for chaos. Thank you, Mr. Smale. Smale realizes that it is not always necessary to know things exactly in order to understand them. A distorted picture is often enough to recognize a face. He shows that the horseshoe is stable. Mind you, this does not mean that the trajectories are stable. On the contrary, trajectories are very, very sensitive to their initial conditions. What we mean here is structural stability. Distort Mr. Smale's picture and you will still recognize him. On the right, we have the original horseshoe. On the left, another horseshoe, slightly modified, is being formed. After all, when you stretch the square into a rectangle and then fold it in the form of a horseshoe, you can do it in any one of many different ways. This is somewhat analogous to the situation where we study two solar systems where the planets have slightly different masses. two almost identical horseshoes. We can do exactly the same as we did with the original horseshoe and draw strips, A' and B'. And it can be shown in the same way that the trajectories on this new horseshoe are still described by sequences of A' and B'. The modified horseshoe is just as chaotic as the original one. Chaos is really there, indestructible. In fact, Smale shows that the movements on the two horseshoes are somehow identical. Look, the two trajectories, right and left, follow the same choreography. They visit the same A', and the same B'. We can match any trajectory of the second horseshoe to some trajectory on the first horseshoe and vice versa. It is in this sense that the structure is stable. We can deform the horseshoe any way we want, and not only does it remain chaotic, but it keeps the same dynamics as before. Individual trajectories are unstable, but the dynamics as a whole is stable. Early in the 20th century, Poincaré, with characteristic flair, explained how it is possible to understand a dynamical system even if one does not know it very well.
You ask me to predict the phenomena that will occur. If I had the misfortune to know the laws of this phenomena, I could only get there by intractable calculations, and I would not be able to give you an answer. But as I am so lucky as to be ignorant of them, I'll answer right away. And what is most extraordinary is that my answer will be correct.
Coexistence of chaos, and hence the instability of individual trajectories, with structural stability, a global property, is absolutely remarkable. I'm unstable, but the world around me is stable. Very reassuring.